Welcome back to another video on linear algebra. We're gonna carry on with the last lecture with linear combinations, spans, and bases, and do quite a lot of examples. Since there's a lot of ways to ask about the span of a matrix, and then as well as finding the bases, and then lastly the linear combination, which those are pretty straightforward, but for the most part we're going to be focusing on bases and spans with one or two, I think it's like two examples on linear combination. So let's get right into it with the first example. So the first example asks us to find the bases for the set of a 3x3 skew symmetrical or skew symmetric matrices. So for those of you who don't remember, which I mean, to be fair, it was like at the very beginning, a skew matrix or a skew symmetrical matrix is symmetric in such a way that, I believe, the matrix, if you take its transpose, it'll be the same thing as the original matrix times negative. So a couple of examples are, we have 0, 2, 3, negative 1, 0, 0, negative 2, negative 3, 1. Another one could be like, I don't know, 0, 4, 6. This would be negative 4, this would be 0, be, I don't know, 9. And this would be negative 6, negative 9, 0. So as I'm making these examples, there's a couple of things that you probably noticed right away if you don't remember what a skew matrix was. The first one is, well, I will show you in the last example. The first one is the main diagonal are all zeros. And then in the bottom left portion, it will just be pretty much any number. So I'm gonna start with the top right. Any number, 1, 2, and 3. And then the bottom left would be the same numbers, but they're negatives and they reflect across the diagonal. So we can write a general matrix of a skew matrix or a skew symmetric matrix. So in general, we'll have a matrix A, B, C, D, E, F, G, H, I, where A, E, and I are all equal to 0, and B is equal to negative D, C is equal to negative G, and then F is equal to negative H. So what we can do now is we can begin substituting these variables back into the general equation, and it'll make our lives much more simpler. So we have 0, we have B, we have C, and then B is equal to negative D, so D is equal to negative B, another 0, and then F is equal to negative H, so that means negative F is equal to, no, that's not, no, this is not negative. This is F. G is equal to negative C, and then H is equal to negative F. Ooh, that's a terrible F. And then last 0. What we can do now is, like, to find a basis, we can just pretty much factor this out into a combination of the variables. So we'll have B multiplied by some matrix plus C multiplied by some other matrix plus F multiplied by another matrix. And so once we factor those out, we can see that it's just pretty much putting a 1 or a negative 1, because we have a negative, a 1 or a -1 where that B lies on, or C or F. So in this case for B, we'll have 0 and then 1 and 0, -1, and then zeros all the way. And then this would be 0, 0, 1, then zeros, then -1, then 0, 0. Then lastly, we have zeros with a bunch of ones and then -1. That's not supposed to be a -1. -1, 0. And we know it's true because if we would have put this, we would have just kind of like plug it back in. We'll have 0, -b, 0, b, 0, 0, 0, 0, 0, plus 0, 0, -c, then column of zeros, and then c, 0, 0, then lastly 0, 0, 0, 0, 0, -f, 0, f, 0. And so when you add all these two together, you can see that we'll have our b's where they're supposed to be, and our c's where they're supposed to be, and then lastly our f's where they're supposed to be. Because remember, when you add matrices, you just add the elements in that specific location. And so our bases will pretty much be everything that's not being multiplied by some or everything that's being multiplied by some variable. So in this case, it will be this portion, and this portion. So the answer to our question, the bases for a skewed, not for a skewed, because that's the general, for a 3x3 skewed symmetrical matrix, that will be equal to our 0, -1, 0, then 1, 0, 0, 0, 0, 0, and then 0, 0, -1, 0, 0, 0, 1, 0, 0, then finally 0, and zeros with the -1, and 0, 1, 0. And that is our answer. And if you want to find the dimension of the bases, you just count them off, which would be 1, 2, 3. So that'll be your dimension. Alrighty then, I'm going to end this video right here. Mostly because the next example is gonna be not hard, it's just gonna be a lot more work, so I don't want to take up too much time in one video. So just, I mean, I could go ahead and pull up the next example. You could go ahead and try it before I upload this video. So this next example, we're gonna let A equal to some 2x2 matrix, and we have to show that there exists a set W of a matrix that consists of 2x2 matrices that's in the real number domain that commutes with A and is a subspace of that M2R. And what makes this a little bit complicated is the fact that it has to commute with A. And so if you remembered back when you guys were younger, it's really hard, or it's not that it's really hard, it's matrices can't commute with each other. It's not always the case. And so we're gonna go ahead and work this example in another video, which will be the next video. But until then, I hope you have a great day, and I'll see you in the next one.